Hi, folks. So my name is Isabella, and I'm really excited to be here today. So first, disclaimer: the name of this presentation is like actually a little misleading, because like we started this thinking that we'd be all over the FPUs things in the AMD GPU, but we're not. So with that out of the way. Well, I'm a Red Hat software engineer. This has actually nothing to do with the work here. I also study at the University of São Paulo, so we are all Brazilian. And I'm actually now conducting a work on the open source GPU stack stuff. So it's actually pretty weird to see that like we're always talking about Vulkan and stuff here, but people actually just use CUDA, and that's pretty sad. So I am finishing my bachelor's in molecular sciences, and that's a weird course, and I don't expect you to know what that means. So together with me, I have Magali and Maíra. So Magali actually also studies in the University of São Paulo. She is doing some research in the introduction of KUnit in subsystems in the kernel. And Maíra also studies in the University of São Paulo. She is with Igalia on the coding experience. And she's researching some, I don't know, how can I say that? So like what's the minimum effort you have to do to have real-time applications running in standard kernel? So we are all in the X.Org team, the same Google Summer of Code team, if you don't know what that means. And we have a friend, Thales, who could not be here today, but he presented a related talk in the Linux Plumbers conference. I don't know if you saw that, in the kernel testing and dependability track. So that's it. Before we continue, we'd like to make a huge shout out to all of these names here. So AMD, like they donated GPUs to us. It was awesome. And we also would like to thank our mentors. So we have Rodrigo Sequeira from AMD, Melissa Wen, and Andre Almeida from Igalia. Thanks a lot. We'd also like to thank KUnit engineers and the AMD engineers that helped us a lot in the process with reviews and feedback. And of course, the X.Org Foundation. Well, we are here because of you. So we'd also like to thank Google Summer of Code and the University of São Paulo. And now, Maíra, the stage is yours.
Okay, so first I would like to make a small review on testing, explaining the different types of tests that we have, explain the importance of unit tests, and also what is KUnit. Testing is essential to a healthy code base. Tests help the maintainability and the robustness of the code, helping us to assure the correct behavior of the system. But not all tests are the same. First, I must say that each test approach has its importance and validates a different type of behavior, so there's no test more important than other. The test pyramid can help us understand those different types of tests. And the test pyramid is like a metaphor that tells us to group software tests into buckets of different granularities. It also gives us an idea of how many tests we should have in each of these buckets. I didn't create this pyramid. It's widely available in software engineering books and in test-driven development books. So if you want to check it out, you might look in these books. In the top of the pyramid, we have manual tests. Manual tests are usually test cases that are executed manually by a tester. This is the only type of non-automated test in this pyramid. So it should be only used for test cases that cannot be automated, because this kind of tests doesn't scale very well, because it can be very time consuming to run thousands of tests manually. Next, we have end-to-end tests. End-to-end tests test the system the same way a real user experiences it, trying to simulate a user's step-by-step experience. This concept might matches better on web applications, where we can have like a test case that covers from the UI to the database, such as a test case for registration in an e-commerce website. But in the graphics stack, we can think about RenderDoc and GFX Reconstruct that are testing tools that can help us to evaluate performance for test cases based on the user's experience. Next, we have integration tests. Integration tests test a particular functionality of the system that has dependencies on other functionality. The goal of these tests is to check the communication and the connectivity of the systems, of the components in the system. In the graphics stack, we have the famous IGT, which has many test cases, most of them being integration tests, although there are some unit tests in it also. IGT really help us to check the user space APIs for the DRM drivers, but sometimes it can be hard to track down failures to the kernel changes. This happens because here we are talking about black box testing, which means that we cannot see inside the box. We can only see the events that come in and out of the box. We cannot see how the elements communicate inside this box. So finally, in the bottom of the pyramid, we have unit tests. Unit tests are the finest granularity of testing. So this means that we can really test all possible code paths. The goal of the unit tests is really to evaluate having some confidence in the behavior of each isolated unit of code. So here we are talking about white box testing, which means that we can see inside the box here. So why introduce unit tests into the Linux kernel? Basically, we are thinking about avoiding regression is the greater benefit from unit tests. As developers, we end up spending a lot of our time tracking down regressions in the kernel. And it would be great to have a tool that points you where the error is. This would really reduce the time that we spend tracking down regressions. And then the developers could focus more in the development of new features. Also, with a proper testing stack, we can even avoid that those regressions end up in the production branch. Also, unit tests can really help refactoring the code. Developers will have more freedom to refactor code without the fear of introducing regressions. This can really help us to have a more healthier code base with periodic cleanups and refactors. As I said before, unit tests also help us to assert the behavior of small pieces of code, which means that we can assure the behavior of simple artifacts of code instead of checking complex behaviors such as in IGT test cases. But there are some trade-offs. First, I must say that introducing unit tests into the Linux kernel means more code to maintain, but the gain in maintainability is so higher that the benefit overpay the cost. Moreover, writing good tests demand time and effort. But once you write them, you can be confident that the regression won't be back again. And another important question might be, why haven't we introduced unit tests into the Linux kernel yet? To put it simply, we didn't really had a framework to do it until now, but now we have the kernel unit testing framework, which is KUnit. Also, for companies, unit tests means a great business value. As you can see in this chart, based off the book Applied Software Measurement Global Analysis of Productivity and Quality, testing with unit tests means that catching a defect with unit tests is 160 times less expensive than catching the same defect on the production branch. This means that if you spend $100 fixing a bug with unit tests, you would spend $16,000 fixing the same bug on the production branch. Also, you can see on the orange line of the chart that with a proper testing stack with unit tests, functional tests, and system tests, that most defects can be found in the testing phase of the software. So this would really help companies to save a lot of money. And as I said before, unit tests are the finest granularity of testing, and as such, is a cheaper alternative for companies for catching defects. So now let's run a bit more on KUnit. KUnit is the kernel unit testing framework, and it was introduced in mainline in 2019, and it was created and is currently maintained by 2 Google engineers. KUnit is currently growing around various subsystems such as the FAT file system, the Thunderbolt driver, and also the DRM. KUnit focus on white box testing, which means that the tests can access internal APIs instead of user space APIs, such as we have in IGT test cases. And KUnit was inspired by some user space testing frameworks, such as JUnity for Java, Unit Test for Python, and Google's Test for C++. Writing tests with KUnit has some great advantages for the developers. First, we can test hardware agnostic code. As developers, we know that sometimes hardware is not accessible, and having a way to test the software without the hardware can be great. You can run the tests as a user space process with UML virtualized inside QEMU, and even deploying it to the hardware itself. Also, this can make CI cheaper and faster because you don't need these huge GPU farms to run the tests. You can run the tests like in a simple laptop or your home desktop. Moreover, KUnit can be integrated into other platforms, even Windows through the Windows subsystem for Linux, and can be even integrated into IGT, as Isabella is currently doing right now. The ease to integrate KUnit into other platforms is a consequence of the ease to build and execute the tests in Linux. Basically, KUnit provides us a Python script that help us to build and run the tests in just a couple of seconds. Moreover, KUnit provides very little boilerplate, and we can have a test ready in just a few steps, as Isabella will show you right now.
Okay, so now we are going to look at a minimal code example using KUnit. So here we have pretty much a textbook example. So on the left, you have a sum function that has a little header thing. And on the right, you can see the actual test file that we would write for that. So it's really simple. We just take two integers, sum them, and return the result. And first thing we do when writing a test is we include the KUnit test header, and then the header for the function we want to test. For static functions, this would, of course, be a little different, but we can talk about that later if you guys are interested. So next thing, we have our test function. So we can just use one in this case, but of course you could split that in lots of functions. So first thing, you take in the KUnit test struct that has like, if the test passed, all the sorts of information, then you feed it into a KUnit macro. So we have expectations and assertion macros. And this one in specific, we are using the _eq macro. So we're testing for equality. First thing, we are testing basic properties we expect this to hold. So a sum has to have like a no element and stuff. Then at last we test extremal value, so just to see if this won't explode. Now we have some KUnit boilerplate. In this example, it looks like half the file is just boilerplate, but in an actual test, of course, this wouldn't be the case. So we have this list with the KUnit cases, and then we can separate each step that the test will run. Next thing, we have the test suite, the KUnit suite struct, which has metadata for the test, and then you can see it when you run it. And then we have the KUnit test suite function, which is like a module init thing. And that allows you to build this as a module or whatever you want. Now, we have a case of study. This was actually sent for AMD, and I wrote it. So we are testing the display RQ DLG cock, and that's DCN20's FPU thing. So this is a pretty simple function, as you can see. We're just getting a source format class enum and a Boolean. And we are doing like if and else to test if it is a certain value, then we return a certain thing. And of course, this relates to the amount of bytes each enum, each format would have. So this is pretty simple. So it's a great example of what you can do with KUnit. And of course, as engineers, we want to avoid accidental changes to this sort of thing. Like this should be set on stone. So this is an excerpt of the test I wrote. So it's pretty easy to understand, like each line is a test. And here we're using assertions instead of expectations because we want to fail as fast as something wrong happens. You can check the full thing in the QR code provided. So here we have 3 pretty simple examples. So we know basically that these values should be returning this stuff. So you can see here in the assertions, like we are calling the function and checking the result just after. And we can also use a more informed approach, like if we have the access to the enum definition, like I did here, I can just look that there are some values that are assigned to others. So dm-mono8 is actually assigned to dm444_8. So I can check that those match. And I can also check some other values that I expect to match, like dm422_8 with a Boolean set to false and then true, they should match. Now Magali is going to take a look at another case of study.
So during the development workflow, we may often wonder what are good situations where KUnit or unit tests in general may be valuable for us. And to answer that, we prepared 2 real-life case scenarios to answer this question. So the first one is this one, which is catching regressions with KUnit. We are going to talk about this DCN21 update BW bounding box case. So this is a function that is found under the display driver from AMD, specifically under the DML folder, which is supposed to contain floating point operations, files and stuff. So the first step is, the first thing we have to do is identify a problem. So in this case, this function triggered the stack size warning. So whenever we would compile the kernel, we would get these compilation warning. And naturally, there was an attempt. And so from this problem, someone tried to fix this problem naturally. And this solution ended up introducing a regression. And after someone noticed that there was a regression introduced by trying to fix this compilation warning, a new patch was sent to fix both the regression problem and the initial compilation warning problem. So from this, we can try to answer the question how to include unit tests in such development workflow. So the first step is we have to identify a problem. In this specific case, there's a global variable that is being constantly overwritten, and depending on the situation, this can cause some important values to be lost. And after we identify the problem, we can write a test case since we know where and how this function is not working as it is supposed to be. And we wrote a test case, and as you guys can see, this is the output that KUnit provides with the expected values and the actual values. And also, we can see the failure. Now, the next step is we finally fix the code, and we also run the test that we just wrote to see if it is now passing. And this is the output that KUnit provides for passing test cases, and that's it.
So now to our third case of study, another regression-based test with KUnit, now on the CDMUB. First, we had a problem in the populate sub-VP CMD DRR info function, some 32-bit compilation errors due to floating point operations out of the DML folder that Magali just told out. And there were attempts to fix this problem that ended up introducing a regression that zeroed all the values in the struct, which was not ideal. And finally, a patch had to be sent to fix the regression and the original problem. As you can see, this is not the most ideal workflow. Of course, the ideal workflow would be to have a problem and then a fix, but we know that this is not possible. So how can we include unit tests in such a development workflow to make it more ideal? We can think about a workflow where we have a problem and then an attempt to fix, you run the unit tests, the unit test will catch the regression, and then you attempt to fix again until all tests pass. And finally, you push your patch when all tests pass to the branch. This workflow is not ideal, but at least the regression will never ended up in the code base. So this is great. So now let's jump into this third case of study. Initially, we had a problem in this function. As you can see, there are a lot of floating point operations. And for those who are not familiar to the AMD GPU code base, there's a folder, the DML, as Magali told it out, where floating point operations are allowed. It's okay to have floating point operations there. But this function is not inside the DML, it's inside the DC folder. So those floating point operations shouldn't be there. And they were causing some 32-bit compilation errors. So those divisions were replaced by the div64 function. And as you can see, it looks okay. I mean, by just looking at it, looks like the function preserves its behavior. But this fix ended up introducing a regression. The behavior of the function was not preserved, and the min vtotal supported and max vtotal supported value ended up being zeroed by this patch. So we decided to write a test case based on the behavior pre-regression, and all 5 test cases that we wrote are failing as expected. And as you can see here, there are 2 important things to notice here. First, it's very easy to see the output of the function and the expected output of the function. So you can think about a workflow, a test-driven development workflow, where you can run the tests in your laptop and you try to make a fix, you run the tests again until all tests pass. And you can be sure that the function that you wrote is behaving exactly as you expected. And if it's not, you can see very clearly what is the output of the function and what you expected. Also, in the bottom line of the log, you can see that all tests build and run in just 6 seconds. So it's fairly fast, and you can run the tests many times, and it won't be very time-consuming. So finally, we reverted the regression, and we checked that all 5 test cases are passing as we expected. So Magali will explain you how to run the tests in your computer right now.
So after seeing why use KUnit, you might wonder how to run KUnit, and this is what we're going to show now. So we listed here 3 options. The first one is to run KUnit on user space. So KUnit provides a Python script under the Linux repository, and you can just run this line, and it'll run on user space, that is user mode Linux, as a standalone process. So currently, this is not supported on AMD GPU, but we decided to point it out since this is the simplest way of running KUnit tests. Also, the second option is to use that same script to run KUnit using a VM. So the only difference here is that you're now passing the architecture as an argument. And this is actually the way that we have been running KUnit for most of our project. Now, the third option that KUnit provides is the ability to run it on hardware. So that means that you can build KUnit into the kernel and install it, and you can have it either as built-in or as a module. So if you have it built-in, on boot time, the tests will be run, and you can check the output on the kernel buffer. And if you decide to have it as a module, you can just run that line to load the module and also check it on the kernel buffer. Now, another interesting thing that KUnit provides is the ability to have test coverage using gcov. So test coverage, in summary, is a metric that shows us how much of our source code is covered by tests. And it also is a very interesting tool that may help us identify files that with missing coverage. So for instance, suppose you have a file that has been presenting lots of problems, and then you notice that it has low test coverage. So that is a very strong indicator that that file may need more tests. So these are the results on the screen from the coverage that we achieved during the project. As we said, we mostly focused on the DML folder, which is on the bottom, and also on the DMUB file. So these are the results that we get using KUnit and gcov. Now, as we reached the end of the project, we decided to summarize some of the things that we know now and some of the things that we still haven't found an answer to. So what we know, it's reasonable to test static functions. So this was a discussion that we have been having for quite some time during our project, because some books state that it's not very nice, must I say, to test private functions. We should instead test the public functions that call those private functions, but this would increase the complexity of the tests. So we came to the conclusion that, yeah, we can test static functions because we don't want anything very complex. Now, onto the things that we don't know is how to test static functions properly. So KUnit does offer an option to test static functions, but it doesn't have a general agreement whether that form of testing static functions is okay or not. So what we know now is that it is easy to run unit tests without the specific hardware. So we actually thought that we would need an AMD GPU to have the unit tests running, but we found out that no. Our unit tests are really making use of the word unit, so there's really no need to have an AMD GPU. So no need to have the specific hardware for that. Also, in the beginning of the project, we thought that we might need to make some device mocking, and it is just like the point above, not really necessary. Our unit tests really follow the word unit here. Now, onto the things that we don't know. With the conversion of the K-self-tests in the DRM subsystems, these K-self-tests, they could be run using IDT. And with the conversion of them, we have come to the question, do we still want to run those KUnit tests inside IDT, or do we want them to be run as a standalone? So we pointed out here some pros and cons of running inside IDT. Basically, the first con is that these are what most companies have. Most companies already have a CI infrastructure that allows the tests to be run through IDT. So if we allow KUnit tests to be run inside IDT, it is easier to integrate into this already existing infrastructure. But the thing is, KUnit already offers a script to run the tests. So why would we need to have IDT to support this as well, since it's one more piece of code to maintain? And the last question is, we have the tests inside AMD GPU module instead of having one specific module for the tests. The thing that we haven't come to a conclusion yet is, should we keep it this way or switch to standalone modules? And what are the implications of both approaches? And that's it. If you got any questions.
So does AMD already have a test, already have a suite of tests, and you're just extending it for the use of? Since you're adding to the AMD code base, you're adding tests to it, right?
So the question was if AMD already has a suite of tests and we are extending it or not. So from what we know, AMD already does tests with IGT, and they have their own suites for other operating systems. But then we are lacking many tests specifically in this front in the FPU code, because like Linus doesn't like it, and so AMD is kind of on its own to maintain that kind of infrastructure.
Sorry, it doesn't like tests. It doesn't like.
Oh no, I meant Linus doesn't like FPU code in the kernel.
Oh.
Yeah. Any more questions?
Why can't you run the AMD KUnit stuff from user space?
So the question is, why can't we run KUnit on user space? I think Maíra.
Okay, so there is a couple of guards in the AMD GPU code that is basically for config x86. And the config UML has config x86 also, but doesn't have the specific structs, field structs for x86. So it's a very simple patch. I wrote it a couple couple of months ago because the test coverage only runs with UML. So we wrote like in a side branch. It's a very simple patch, just adding like a OR in the guards. So if just skipping these guards if it's UML. But there was a discussion a while ago if we should introduce UML into the AMD GPU. And it would be one more architecture for AMD to maintain. So we are not sure if we are going to have UML in AMD GPU. But it's a possibility. It's like a 10-line patch. It's a very simple patch.
Just to make a parenthesis here, we're talking about UML because that's what KUnit runs on user space. So, yeah.
So regarding integration with IGT, on the Intel drivers, they have a single IGT test that unloads the kernel module and then loads it with the parameters required to run the unit test. They call them self-tests, but unit tests. And then it's able to scrape the message and turn that into IGT results. So you don't actually have to keep anything in sync. There's no additional list of tests that live in IGT. It's just a single test that just runs everything and then reports the test results so that you can run that in the same CI structure as you run all of your live GPU tests. So that's, if you want to do integration in order to be able to make sort of a CI situation better, that's one way to do it. I don't know if you've seen that or looked at that. But, Intel calls them self-tests, which is a little bit of a different name, but if you search for that inside IGT, you'll find the test that does that. It's pretty simple.
Okay, so that wasn't really a question, but Giselle pointed out that Intel already had a pretty nice solution for running unit tests inside IGT. So yeah, there's that. I'm not aware if that is using KUnit though, is it?
No, it's a custom handle.
Oh, okay.
Okay, but the problem here, like Isabella is right now writing a parser for the KTAP because KUnit may just give you a KTAP, like a log that we need to parse. Currently, IGT has IGT self-tests, which parse the results of the self-tests. So the problem is like to maintain another parser because the KUnit tool has a parser wrote in Python, and we need basically to maintain another parser in C that Isabella is doing right now, if you want to talk more about it.
Yeah, so I wasn't aware that you were talking about the case of testing, but yeah, that's exactly what Maíra said. So we actually already have somehow of a parser, and we can use pretty much the same infrastructure they already have for this, but we need some other tools because KUnit try to make their I don't know, report style, like TAP, that's a test anything protocol, but for the kernel. So that's KTAP. That's how they call it. And so we're implementing that. And it would be a very similar solution to what you said, but it needs a whole different, yeah, it needs a whole different parser. So go on.
Yeah, first of all, thanks for trying to, for teaching us how to improve our messy code and some, the stuff that you've discovered there, which is great. In regards to self-tests and IGT and all that, I really like that KUnit, at least what you've done, it's unit testing without needing hardware, right? And so it doesn't need, I guess from that standpoint, I would prefer if it stays separate from IGT because IGT requires real hardware. KUnit you can run quickly with quick turnaround even if you don't have UML. Like you say, 6 seconds to build, boot up the emulated environment and test it. So I think from that standpoint, my preference would be to keep it separate.
Okay, so what he said is that he would prefer to keep it separate from IGT because IGT depends on real hardware. So yeah, we agree with that. And that was something that Michal Winiarski already pointed out in the mailing lists. So we are aware of that, but that's why we're bringing up this discussion, because we're working with AMD, and for them it would be very profitable to bring that to IGT, because it makes their life a lot easier to integrate with their already existing CI, because it would be like just more, I don't know, 2 seconds to run those tests. So it would not be so much of an overhead, but of course you could utilize real machines better. Any more questions?
Yeah, so thank you for doing this. For another project that I've been working on, I've been trying to do device mocking using KUnit, and let's just say I ran away and decided that it was actually easier to take the Lemes interface and re-implement that in the user. So not a nice thing to do. So I was wondering if you have pointers on how to do device mocking, or if you thought about it, or yeah.
Can you get that?
You can say no. Okay, so Martin's answered that, asked that, like if we could, we have some inputs on device mocking, because he tried and he wasn't very successful. We didn't, like in the first couple of weeks in Google Summer of Code, me and Magali were working on device mocking. And there is a patch currently in the KUnit list. There is doing some platform device mocking, but we didn't really explore it because we didn't really need it. We discovered that it wasn't really necessary for the AMD GPU code. Probably for other applications is necessary. And I believe that the guys at Google, like David Gold and Brandon Higgins, are currently working on it. They are also working on mocking functions. So you might use this maybe.
So we have a question from the live audience. Did you find any particular advantages to running KUnit under UML over QEMU, other than the code coverage support?
So the main advantage is really running it in user space. So that's a lot less. It asks a lot less from the hardware itself. You don't need any virtualization. You can just run it on the kernel that you already have. And that's the main advantage, really, apart from timing. It is really quicker. But I don't think there's much more else than that. Yeah, and the coverage that I already mentioned. Anything else? Okay.
So what's your goal with this? Are you going to continue, or do you think that this project is done?
So the question was if we're going to continue with the testing and stuff. So it was really exploratory work. We did not do so many patches, but we laid the groundwork for it. We hope that AMD engineers do it themselves as well right now. But we, of course, if we see something that can be improved upon with, I don't know, an okay amount of effort, of course we're going to do it. Yeah, and we are also looking for mentees to continue the work, maybe on other subsystems as well, not only on AMD GPU. You're welcome. Okay. So that's it. Let's wrap it up.